Today we have a special privilege to welcome Jeff Puschell. I'm going to say the last name fast. With extensive experience, so this is going to be a great talk. He has quite the intro, and we could spend most of the talk me reading it, but we won't do that. And I'll let him speak for himself when he starts his talk, but I'll just give you the highlights, okay? So Jeff Puschell is Principal Engineering Fellow at Raytheon, Space and Airborne Systems in El Segundo, California there. And he mainly works in system engineering, space-based imaging, remote sensing. He's been doing this for a number of years, 30 plus.
Mm-hmm. We'll say how many plus beyond that.
Right, 30 plus is good, 30 plus is good. V-near instruments, space-based, operational, remote sensing, laser bed communications, remote sensing systems, millimeter, IR, viz, UV, looks like you name it. Based on astronomy, ground-based astronomy. He's been chief engineer, chief scientist, technical director, dozen major projects, space-based remote sensing. Served on a lot of advisory boards, NASA, Department of Commerce, a lot of review panels, NASA, NSF, DARPA. Again, these are just the highlights. Over 130 papers, co-authored a book, Space Mission Engineering, holds a bunch of patents, led some societies in terms of SPA, AIAA, I think that's American Institute
of Aeronautics and Astronautics.
Yeah,
Mm-hmm.
yeah. Associate editor, SPA JARS, so those of you writing papers for JARS, you'll see it. Chair for SPIE Remote Sensing System Engineering Conference, April?
Actually, August.
August, San Diego?
San Diego.
Okay,
Yeah.
there you go. And he also teaches. Raytheon, there's a paragraph in here about that, but I'm only going to read a single sentence. Raytheon Professor of Practice at Cal Poly in St. Louis Obispo. And he's undergrad in physics, Chicago, PhD astrophysics, Minnesota, SPA fellow. And he is in California now, Hermosa Beach, and in El Segundo. So take it away.
All right, thank you very much. Thank you for that very kind introduction. I'm very pleased to be here today. I've spent the whole day here and I've enjoyed it. Very impressed by everything I've heard about today. I don't know what our usual protocol is here, if you take questions in the middle of the talk or wait to the end.
I don't know. Traditionally, we kind of wait towards the end, but if it's something super pressing, it's I don't think you would object if somebody.
I would not object.
So.
Okay.
Either way.
Let's go.
Paul.
So, I am from Raytheon. I'm a principal engineering fellow, and I'm also the PI for something called Atlas, which I'm going to be talking about today for a few minutes. Really, most of my talk is about the future. I tend to live in the future, and I can't really tell you what the stock market's going to be in 2024, but I can pretty much tell you what I think the government will be doing in certain areas of space-based remote sensing. It'd be only a wild guess, and it's probably going to be wrong, but at least that's the kind of world I live in, thinking about the future. This is a Landsat 5 frame collected with Landsat of Rotterdam in the Netherlands, collected in 2006 by Landsat 5 Thematic Mapper, which still holds the Guinness World Record for the longest operating space-based imaging remote sensing system. I want to tell you just a little bit about Raytheon, mainly because it seems like when I travel, I'm always surprised that people don't know what we do, even in places like this that are extremely well informed. So we've been in the space-based imaging and remote sensing business since the mid-60s. We built the very first geostationary weather imagers. We were the first in many other areas as well. What this slide shows is results from some recent systems. In the upper left is the so-called dark marble that NASA put together a few years ago, showing what the Earth looks like at night from space, based on data from VIIRS, which is a 22 spectral band imaging spectroradiometer. It's multispectral, so it really doesn't have a grading or FTS system or any other kind of imaging spectrometer built into it. But we call it an imaging spectroradiometer because it's very well calibrated. And one of the bands inside VIIRS is this so-called day-night band, which is a high dynamic range 750-meter resolution, so not really high resolution, but very sensitive band for looking at clouds during the day, the brightest clouds, and also being able to see clouds at night, illuminated by the quarter moon, illuminated by air glow, and illuminated by city lights. And it's used for a lot of different reasons. It has legacy to the DMSP program, something called the Operational Line Scanner. That was really first developed decades ago, unbelievably, using photomultiplier tubes, really an amazing instrument for its time. In the upper right is another example of VIIRS data. It's actually from a typhoon in the Pacific, and you can see the very high spatial resolution in the infrared of the VIIRS data. For a weather imager like this, it has the highest spatial resolution. And combined with its sensitivity and very well highly calibrated system, it provides data that's extremely useful for numerical weather prediction. Lower left is Landsat 7 ETM Plus data of Greenland. And finally, in the lower right is the same typhoon as observed with VIIRS, but in this case it was observed with something called MTSat-1R with JAMI, the Japanese Advanced Meteorological Imager, which was in geostationary orbit. And I'd like to show these two things together because of the contrast in information that you get from these two different systems. In the case of the geo system, you really get a sense of the timeline, where the typhoon's going, what the impact is. In the case of the VIIRS data, of course, you get much higher quality data, higher spatial resolution, better calibration, more information, but you only get it once or, twice a day in the case of the emissive bands. So two different kinds of information, both valuable in their own way. Of course, I've been involved with both VIIRS and JAMI, chief scientist for VIIRS, one of the chief engineers for VIIRS, and I was chief engineer for JAMI. Video overview of the Landsat program. I don't know who picks the music for these videos, but you just have the sense that something important is about to happen. The world's going to end, or something, or really maybe something really good in this case of Landsat. So as the video said, Landsat's been operating since 1972. It's the longest running program for acquisition of Earth imagery from space, and it was the first space-based land imager. You saw some of the missions highlighted in the video. It's amazing what Landsat gets used for. Mostly intended for land surface, but used more recently for coastal, for looking at coastal regions. A lot of that work's been done here by John Schott and others here at RIT. Mostly used for monitoring biomass, vegetation. We built the first 7 land imagers. Landsat 8 was launched in 2013 with the operational land imager, OLI, built by Ball, using Raytheon focal planes. It covers the visible through the shortwave infrared. And then another instrument called TIRS. And I hate to make jokes about instruments, but sometimes I think that acronym is appropriate. The tiers that have been created in some cases by, by some of the early results from that instrument may be appropriate. Today we have a 2-satellite constellation, Landsat 7, which has ETM+, and Landsat 8. In the future we'll have 8 and 9, and that's coming up here before we know it. As I mentioned, this is ETM+. Actually, this is the thematic mapper, I guess, according to the slide, and some data from Landsat 5, taken, I'm not sure when it was taken, come to think of it, but it was, this system was launched in March of '84 and was decommissioned just a few years ago. Let's look at the history briefly, and I thought I should provide this kind of background information, even though I feel like I'm giving this talk in one of the real centers of expertise for Landsat. But nevertheless, I think sometimes it's good to go back and look at some of these things, and perhaps some of you are not that familiar with the history of Landsat. So you can see at the beginning, the resolution was about 80 meters. The orbit was higher than it is today. Today, the system flies at 705, and back in the beginning, in the early 70s, it flew at an altitude of almost 920 kilometers. Over time, the system got progressively better, going from 80-meter spatial resolution at the beginning down to 15-meter pan data, 30-meter multispectral data with Landsat 6. And I should mention that the thematic mapper data became 30-meter with Landsat 4. Landsat 6 ended up on the bottom of the Southern Ocean, unfortunately. It was not successfully launched. And so there was it was good that Landsat 5 turned out to be such a robust system because it was needed to get through the gap and beyond between Landsat 5 and Landsat 7. 7 went up in 1999. I was actually there for the launch. I missed the launch of 8. I was actually on an African safari in February of 2013, but I certainly followed it with a lot of interest. Today the system has 15-meter pan resolution, 30-meter multispectral resolution. Landsat 7 had 60-meter resolution in the infrared, thermal infrared, but with Landsat 8, it took a step back to 100 meters. Now, in my experience of many decades working on programs like this or similar to this, it's very rare to see any kind of step backward like this. And it'll be interesting to see what the future holds. And of course, that's why I'm here today to talk about that future. I think we're going to go back to 60 meters, but we'll talk about that in more detail in a moment. So Landsat 7, ETM Plus, Enhanced Thematic Mapper Plus, has a 40.6 centimeter aperture. And so that's relatively large by the standards of civilian environmental monitoring instruments. And the reason it's so large is that it is needed really to achieve these signal-to-noise ratios in NEDTs, especially the NEDTs in the thermal infrared. So it's not really diffraction limited at 40.6 centimeters with that aperture size, but it's really needed to make up for the sensitivity relative to other systems that have coarser spatial resolution. It's a relatively large system, 409 kilograms, roughly 1 meter by 2 meters in size, 7 spectral bands, and you can see them listed here. Full aperture solar diffuser, and I believe that was the first of the Landsat imagers to have that, and it was preceded by the other systems that we've already talked about briefly. Landsat 7 was a whisk-broom imager, which means that it basically scans the Earth across some swath width. And that swath width is about 185 kilometers. The scan mirror basically goes back and forth, directing the scene from the Earth into the instrument, looking at different nadir angles along the track. There's a mechanism built into Landsat 7 called the scanline correction system, which you can see here, which I really think is a mechanical marvel. It basically moves back and forth to correct for the motion of the spacecraft. So I wasn't sure we'd have a board in the room, so I thought I'd better bring a slide that really illustrates what I'm talking about. It's pretty obvious once you think about it for half a second. As the spacecraft moves along, and the instrument is basically scanning back and forth along the track, as the spacecraft moves, of course, the swath advances along the path of the spacecraft. And on this slide, it's actually going down. So as we're scanning, these swaths become skewed like that. Subsystems are willing to live with that, actually, but Landsat is not, because of the way it was designed. If you allowed that to happen, you'd have these gaps. And that was not acceptable. And so this mechanism basically compensates for the orbital motion of the spacecraft to produce swaths that look like that rather than ones with gaps. Okay. Yes, I just wanted to make sure I covered all the important material here. One thing I should mention, of course, is roughly 4 years after launch, this SLC stopped working. So a lot of good data is still being collected by ETM Plus, but it doesn't have this scanline correction applied. This is what the focal plane looks like for ETM Plus. And one of the reasons I wanted to show this is just to give you a sense of how systems like this were developed decades ago. Some of them sort of resemble this even today, but what you see here is you see the cross-track direction goes from left to right on this slide. What you see are discrete detectors that are in alternating rows. And so this required a lot of manual assembly. They were spaced like this just to make it easier to provide space for the electronics. You have to be very careful, though, how you scan this, because you will have gaps if you don't scan exactly perpendicular to this axis. And for the time, this was a relatively large number of detectors for systems like this. We're talking about essentially 1980s sort of technology, even though this one wasn't launched until the late 90s. It was basically 1980s technology. Has a cold focal plane with the infrared bands, and then a more ambient temperature focal plane with the shorter wavelength bands. 32 detectors for the pan and 16 for the other multispectral bands, except for the thermal infrared band, a single thermal infrared band, in this case with only 8 detectors. Well, this system worked pretty well, but it was realized really in the late 90s that there may be better ways to do the land imaging mission. This Landsat imager was large. It had limited sensitivity despite its size. There was a desire for better sensitivity, and that desire for getting better sensitivity was realized by the advent of improved focal plane technology. So if we go back, one of the reasons I showed you this is I just wanted to sort of make it clear what people were dealing with decades ago, discrete detectors built by hand into these focal plane assemblies. By the time the late 90s came along, we had basically moved almost everything you saw on the previous slide into the microelectronics domain. In other words, we didn't really need as much hand assembly, certainly of individual detectors. We could make the readouts and the detectors in foundries and integrate them together. And that enabled a new type of imager for land imaging that we call a push broom. So Landsat 1 through 7 whisk broom, you can think of it as a spot basically flying back and forth across this swath, where each instantaneous field of view at every instant is looking at a small patch of the Earth, and it moves over that small patch of the Earth literally in microseconds. A push broom imager, on the other hand, doesn't have a scanner. It has a much larger detector array, though, or detector focal plane assembly, really, that is able to dwell for a much longer period of time over each scene element, thereby increasing the signal-to-noise ratio, thereby making it possible to also reduce the aperture size, because if you're limited by sensitivity, you can actually reduce it down to something that's more like the closer to the diffraction limit of the system that you're building or designing in the early phases. The third possible approach, of course, is staring Systems in low Earth orbits typically don't stare. If they do, they face significant challenges during the image motion compensation that goes with that. But there are systems that stare in GEO that are actually pretty successful. So with this new focal plane technology that was really developed mostly in the 1990s, people started thinking about what they could do with land imaging. And they realized that you could go from something like Landsat 7, relatively massive, relatively power hungry, et cetera, to a much smaller system with only 12.5 centimeter entrance pupil diameter or aperture that was more driven by diffraction. And the advantages of going with this smaller system rippled through every aspect of the system: smaller mass, smaller power, higher data rate, of course, you've got more data, but better spatial resolution and much better sensitivity, even at that better spatial resolution. So that led to something called EO1, the Advanced Land Imager, which was built by Lincoln Lab with Raytheon participation. We provided the focal plane modules for the Advanced Land Imager, which was still operating until very recently, decommissioned, I think within the past year or so. It was launched in the fall of 2000. The telescope was made by SSG. Integration and test was also done at MIT Lincoln Lab. I'm not going to go through every detail on this slide, but the main thing I want to point out, really related to the overall Landsat story, is that ALI had a partially populated focal plane. So the idea here wasn't to really produce an operational land imager, OLI. It was to produce a technology demonstration that would then support future Landsat systems. And so that's what it did. Rather than having everything populated, it only had one of the 6 modules. Well, it was very successful. Actually, I was wrong. It was just within the past 6 months or so that it was decommissioned. So well within the past year. Basically, ALI proved the technology for the OLI, and I think the best way to understand the importance of that is to look at this slide, showing a comparison of the same scene taken at 2 different times, both in November though, one in 2000 November, the other in 1999, showing the same scene. This is 10-meter resolution. You can see it's clearly higher signal-to-noise ratio, much higher quality image versus the ETM+, the whisk broom imager, with great history of success, but simply not the sensitivity of this much smaller push broom system. Well, so you might think this would be the end of whisk broom imagers, right? Clearly the push brooms outperform them. Why would we bother to ever go back and look at another whisk broom imager? Keep that thought in mind for a few minutes. So Landsat 8 was a little bit different than Landsat 7, moving more toward the blue with the coastal aerosol band, adding another thermal infrared band. Both these bands are at 100-meter resolution, again, versus the 60-meter that was available from Landsat 7. And I think very importantly, another cirrus band. So now a significant improvement in land imaging capabilities over the previous systems, including ALI. So Landsat 8 flies 2 different push broom imagers. One is OLI, shown here, and TIRS, the infrared system, with detectors cooled at 43 Kelvin. As mentioned already, OLI was built by Ball, TIRS is built by Doug. Let's look at this in a little bit more detail. So this is an illustration of the OLI. Some of the optical parameters that I won't read to you, you can see them on the chart. OLI has 14 focal plane assemblies with a total of about 6,900 detectors in the multispectral bands and about almost 14,000 in the pan band. So unlike the ETM+, it covers only the vis through the sphere. So it does not go into the thermal infrared. You can see some of the detector parameters, 36 micron detector pitch in the multispectral bands, simply meaning that each detector is separated from the center of each detector is separated from its neighbor by 36 microns and 18 microns in the pan bands. And the detectors do pretty much fill that entire cell size. In the SWIR band, it's a bit different, as you can see on this chart. There's an internal shutter, which is an innovation over the previous systems. You can see the shutter wheel here, and you can see the size. Now, you would have thought that if you compare the size of ETM Plus with the Advanced Land Imager, and then compare the size of something that is roughly the same size. It is a little bit bigger. It's 13.5 centimeter entrance pupil diameter versus 12.5 for ALI. You would expect the size to be quite a bit smaller than ETM Plus. But in fact, it's not. It's actually bigger and it's more massive. Power is quite a bit less, fortunately, with improvements in electronics. Quite a bit of the volume that goes with OLI is in this calibration assembly that's at the front end. And so if you were to take that off and compare, say, just the volume of the actual instrument itself without the calibration module, it'd still be quite a bit larger than ALI, but it would be smaller than ETM Plus. This shows you a bit more information, sort of a schematic of the optical system with some more detail really on the calibration system. So it's fairly complex. It has a shutter, as I mentioned already, which is very useful for, and really I think a necessity for a push broom imager. In the case of a whisk broom, you can look off of the Earth and get basically a zero signal level. With a push broom imager, you could maneuver the entire satellite off of the Earth, but I think it's much easier. It makes a lot more sense to have a shutter built into the instrument to be able to prevent light from getting into the instrument, thereby enabling you to measure the zero signal count. It has a couple of diffusers. One is the primary diffuser that's used relatively often for calibrating the solar reflective band. So the sun is allowed to come in from the top in this diagram and illuminate a diffuser which illuminates the full aperture and the full optical path of the OLI to enable that kind of direct calibration against the sun. But because diffusers degrade over time after being exposed to the sunlight, they have another diffuser in there that is called the pristine diffuser that is used only rarely to track changes in the primary solar diffuser. They also have lamps. It's quite an elaborate calibration system. This slide shows the focal plane assembly, so you can see the individual modules. And of course, it's a push broom imager, so the along track direction is basically perpendicular to the long axis of these individual sensor chip assemblies. Performance is good, very good actually with respect to requirements. You can see typically a factor of 2 or more margin, depending on the band. In the case of some of the bands, it's more like a factor of 3 margin, but you can see very good margin really all the way across the spectrum with respect to the requirements. OLI has been an amazing instrument. I really commend Ball for the excellent work they did in developing this instrument. It's collected excellent data. One of my areas of interest is coastal water, and this is data from a Brian Franz et al. Paper from 2014. Brian's at Goddard, in case you don't know him, showing Chesapeake Bay ocean color at very high spatial resolution relative to MODIS, for example, or VIIRS, or CIS. All right, the thermal infrared sensor is a push broom as well, as I mentioned. It has the same 15-degree field of view. That's what you need from that orbit to cover the Landsat swath. It uses QUIP detectors that are cooled to a very low temperature, really, compared to other systems like this, 43 Kelvin. You can see the different parameters. The telescope's passively cooled. Certainly, TIRS is much more sensitive than ETM Plus was in the infrared. So even though it doesn't provide as good of a spatial resolution as ETM Plus, it is more sensitive. You can see the size, so it's quite a bit smaller than OLI, even though the imager is about the same size in terms of its entrance pupil diameter. And the reason for that is a refractive instrument, so you can package that into a much more compact design than a large reflecting telescope like the one in OLI. This is the floor plan for the focal plane. You can see that's kind of a similar approach as OLI and AOI with these overlapping SCAs that cover the full long track direction. Now you might wonder, well, okay, so this is a push broom, so you don't have some of the same effects that you would have in a whisk broom imager with potential gaps forming in the imagery as you scan. And of course, a lot of that depends on the focal plane. The Landsat 8 spacecraft does have to maneuver, has to go through a sort of a slow yaw rotation as it is orbiting to prevent gaps in that data. Okay, well, so that gives you a very quick history of where we are today with Landsat. I'm involved in something called SLIT, Sustainable Land Imaging Technology. And I think this is an example of a very worthy government program. It's an investment in an operational system of the future. What NASA and USGS are doing is enabling several of us to develop prototype instruments, prototype approaches for the next generation of land imaging. The idea is to reduce risk in a relatively friendly environment, not having to worry about space qualifying things initially, testing new technology and trying to establish its value for land imaging through system engineering. And so that's pretty much what that says, basically research, develop, and demonstrate new measurement technologies. So ESTO, the Earth Science Technology Office, which is part of NASA headquarters, but located at the Goddard Space Flight Center, is in charge of this. Sachi Babu is our program manager for SLIT, and we're working with him, Phil Dabney, and many others that you know here in developing something called ATLAS. So ATLAS is one of the several SLIT projects. What we're doing with ATLAS is we're trying to determine whether a very compact, low mass approach for collecting Landsat imagery will actually work. And we're pushing things a little bit in terms of minimizing the aperture size. We think we can maintain the image quality. In fact, we think we can do better in terms of image quality than the existing system with the way we sample the focal plane. We are building, as far as we know, and whenever I talk about ATLAS, I always make this, put this condition on it, because I've been in many talks when I've heard a guy stand up and say, we're the first ones in the world to do this. And I have to be the bad guy that raises his hand and says, we did that 20 years ago. I'm sorry to tell you that. But as far as I know, the reflective telescope that we're building for ATLAS is the first completely free-form reflective telescope ever built by industry in the US. So did I put enough qualifiers on that? That may not be the case, because I could think of some other places that might have done something similar. But as far as I can tell, and we know all those people very well, no one else has come forward and said, no, we've done that already. It's been done in Europe, okay? And even OLI, on Landsat 8 today, has a single mirror that is freeform, but the other mirrors are standard, conical cross-section mirror. So the technologies we're developing and integrating in ATLAS include this wide field of view, nearly telecentric reflective triplet telescope, a production digital focal plane with on-chip processing, a full aperture calibration approach, which we think is much simpler than what is flying today in OLI. And I think in some ways the single most important part of ATLAS is this performance model, where we basically have included every effect that we can think of in terms of predicting the image quality performance of a future land imaging system. We're more than halfway through the project. We've got some of the hardware in-house already. We're expecting the rest of it by early next year. And we should have it wrapped up by by May or so of next year. So, as I look ahead, I look to the future, I wonder, what is the future Landsat going to be like? Is it going to be a push broom again? Is it going to be a whisk broom again, or could it be something else? Well, so I wondered, what is the relevance then of this work we're doing in Atlas, which is being built in response to requirements that are really more driven by Landsat 8 than by a possible Landsat 10. And so as I look at it, I see that Atlas supports a disaggregated architecture, and that's similar to what we're flying today. So we have a separate Viz SWIR instrument and a separate thermal infrared instrument. That's disaggregated, so supports that. Certainly a push broom imager could be built on the Atlas architecture, and that's really what it was based on. But it also supports a full spectrum instrument by basically demonstrating a design that could be scaled up to something larger. So a full spectrum instrument, because of the 60-meter thermal infrared pixels, is going to require a larger telescope than what we're building today with Atlas. And I think it's very likely to be a free-form reflective telescope as well. So everything that we learned from Atlas will be relevant to any future architecture for Landsat. We really see it as a test bed for us and for NASA to experiment with different imaging approaches. And so let me tell you just a little bit more about it. We're going to be able to look at a number of different spectral bands, 6 spectral bands altogether. We can operate it in different configurations, so we can operate it with full frame filters at 865 and 443 nanometers. By full frame, I mean covering the entire focal plane assembly that we have. Or we can also use it with a VIIRS integrated filter assembly. And so we have the VIIRS spectral bands in that part of the spectrum, which are not identical to the Landsat bands, but they're very close. And so we think this will be a very useful demonstration. We're going to measure, of course, sensitivity, signal-to-noise ratio in all of those bands, and also image quality, the relative edge response slope, to be more precise. So Atlas came out of a previous NASA study that we did called the Reduced Instrument Envelope Study. And what we did is we looked at a number of different architectures. We looked at a full spectrum architecture that we called the Compact Land Imager. And so again, this is based on Landsat 8 requirements. So this one has 11 spectral bands covering the visible through the thermal infrared with a 60-meter thermal infrared. So in that sense, it's different than Landsat 8. But with a very fast telescope, f2.5, 17.5 centimeter effective aperture to really provide the image quality we needed at 60-meter resolution in the thermal infrared. We also looked at a disaggregated architecture, something we call the subcompact land imager, which is basically the CLI scaled down by a factor of 2. And then, so that would cover the Viz through SWIR, so sort of like the analog with OLI today. And then something we call the infrared land imager, which is a refractive telescope similar to TIRS in that sense, very compact like TIRS, with a different kind of detector material though, different kind of cooler, but in many ways very similar to the TIRS. But what we found when we did this study is we wanted to compare full spectrum instruments versus disaggregated instruments. We found that CLI, the full spectrum instrument that we looked at, is 17 times smaller in volume than the combination of OLI plus TIRS. So this full spectrum instrument, and there are many advantages to full spectrum instruments, is almost 20 times smaller than the current disaggregated system flying today. But maybe more importantly, we found that the version of disaggregation that we looked at with the subcompact land imager plus the infrared land imager was another factor of 2 smaller than CLI, and so 38 times or so smaller than the current system. So we thought, this is great, this has tremendous potential. We have better sensitivity, better spatial resolution, better image quality. With this much smaller system, this would clearly be the way to go. And that's why we based Atlas on the subcompact land imager. Well, then the story changed. And it changed in a very interesting and dramatic way. I I went to the Landsat Science Team meeting in July at the Aeros Data Center near Sioux Falls, South Dakota, primarily to talk with people about Atlas, but also to really get a better understanding of what is likely to happen with Landsat 10. And it was, frankly, for me, a very eye-opening meeting, because I had some understanding of what was going to happen, but my understanding was improved by who knows how many orders of magnitude as a result of that meeting. What I found very interesting, and I can't really commend the Landsat Science Team enough for doing this, because I've never seen this happen in any other user group. I interface with a lot of user groups across the US government, and I've never been to a meeting where they actually sat down and voted on their priorities. Usually they won't tell you their priorities. You beg them, please tell me, what do you want? And, well, we're not sure, we think we want that, but we'll let you know someday. Well, these guys actually got together, categorized their priorities into 4 broad categories, and took a vote. And what they determined, and this was in the order of priority, they determined that the most important priority was to improve temporal refresh from 1 cloud-free line of sight per month for every land pixel on Earth to about 1 cloud-free line of sight per week. Now this may be an oversimplification, but this was basically what they said. It was more convoluted and complex than that, but that's basically what it was. So if you were to do that with a system like today's system, that would mean going from a system with 16-day revisit time, which is what the current Landsat imagers have, to one with a 4-day revisit time, roughly. Or maybe you could have 2 systems, again, like they have today, with 8-day revisit rather than 16 revisit time. You could also address it with a constellation. And you know, I've looked at constellations for many different applications, and there's no doubt in my mind that you could address land imaging with a constellation of, say, Atlas-like imagers and ILI-like imagers for the infrared, and do this mission. Or you could have 2 satellites with a 31-degree field of view, roughly, well, twice the field of view that we have today. They also want to improve the spatial resolution from 30 meters to 20 meters in the multispectral bands, BISWIR bands, and 10 meter in the PAN. And they want to go back to 60-meter resolution in the thermal infrared. Those are all, to me, very logical, evolutionary, important improvements. They want to improve spectral sampling, either by adding a few bands or maybe changing a few of them to narrower bandwidths, or maybe even making the system hyperspectral. Now I have to tell you, we've been thinking about hyperspectral land imaging systems for a long time at Raytheon, and many others have as well. And I really expected to hear more support for hyperspectral at this meeting, but I didn't. There were some advocates like John Schott who think very highly of hyperspectral and see the benefits of it, but for the most part, this group really didn't see it that way. Improve signal-to-noise ratio to measure Landsat 8 performance. I think that's a no-brainer. It's going to happen. There's no reason to have requirements that are basically dating from the 1980s almost for a 21st century system. Calibration really didn't come up because I think everybody assumed that's going to be there no matter what. The platinum standard of calibration is provided by Landsat. Well, I put this video in, which was provided courtesy of Curtis Whitcock at Boston University, who has been the chair of the Landsat science team during the past year, to really illustrate the importance of going to improved revisit time. Curtis put this video together for a very different reason. But when I saw this, I said, this is the perfect illustration for me to show in this talk, and I've used it in other talks, for why you need to improve the revisit time. So, and his video goes beyond that actually to show some other applications. So let me go back and then start it again. So the first part of the video shows the sequence of successive passes over Boston University. And so you can see every 16 days Landsat comes over, and what does it normally see? Well, I would say that roughly half the time, if not more than half the time, it sees clouds, which means even though you think you have a 16-day revisit time, you have more like a monthly revisit time. And so there are a lot of opportunities to make measurements that are not made simply because you don't come over often enough. The second part of the video, though, shows what Landsat, the current Landsat, is really good for and doesn't require improved revisit time, which is looking at long-term changes. And so this shows data over a period of decades showing how the Boston area has changed in terms of urban development and other things. So very good for that. You don't need better revisit time to do that, but you certainly need it if you're doing agriculture or any other kind of synoptic, some relatively low, quick synoptic monitoring. Well, some of the other things that came up with were, well, let's go to one-day revisit time. Landsat should have that because other systems have it. And it's true, the Surrey Disaster Management Constellation, DMC, has a one-day revisit time. And that's amazing. And this is a very interesting business model too, by the way. Surrey builds all the systems, but they're owned by different people. So Nigeria owns one, there's a Spanish company that owns one, and the Chinese own one. So great idea. There are other sources of data. The Germans are about ready to launch a hyperspectral system called NMAP that might be able to follow up on multispectral change observations, which would be useful for science, but maybe not so much for operational use. Some of the people I talked with talked about 30-meter thermal infrared resolution, and 10-meter vid-sphere multispectral, both achievable, but quite expensive to achieve. Another thing that came up was, should we build another ALI? In other words, a technology demonstrator that would really validate a new approach for land imaging the way ALI did for OLI. Well, on the basis of all that, I came up with these requirements. And they're my requirements. When I talked to somebody from the USGS and said, who is coming up with the requirements for the next system and when, they said, well, one thing we know for sure, we don't know really, but for one thing we know it's not going to be you. And I said, well, don't be so sure, because at the end of the day, it's really industry that really determines what can be built affordably. And there's always competition, competing ideas, different ways of doing things, but at the end of the day, this is a community exercise. And yes, the customer agencies really do determine the requirements, but they're not going to specify something that can't be built by industry, because their program would be a disaster. So it really, we're all in this together, working together to take us to the next generation. So what I think, just based on what I heard and what I think is feasible, is we are going to go with an improved revisit time. 4 days in the visible through SWIR and 2 days in the thermal infrared. And I think what that translates into, I'm going to skip ahead a little bit, is to 2 systems like we have today with 7 and 8, and we'll have 8 and 9 in the near future. This would be with 10 and 11, but each with a 30-degree swath versus a 15-degree swath. So you'd be covering twice the field of view. There's a system, a European system flying today called Sentinel that has 25 degrees. Spatial resolution is going to improve. Spectral coverage, this is the one where I think, in my mind at least, there's perhaps the most uncertainty of what's going to happen. I think they'll probably try to add these red edge bands, which are similar to the red edge bands in European systems like Maris and Sentinel. They may even add other bands in the emissive infrared. It's hard to say, but I think the red edge bands are very likely. Sensitivity will be the OLI sensitivities, and it will be highly calibrated. If you look at what the Landsat 8 imagers have today, they have more than 1,000 requirements. I'm only going to consider a few of them. Well, these are the bands. So it's really what I just told you, the current 11 Landsat bands plus these 3 Sentinel bands. In terms of the radiometric performance requirements, again, I've reiterated the bands. These are the pixel sizes. I don't have, these are the typical radiances, in other words, the reference radiance for a typical scene that the band needs to be able to measure. This is the maximum radiance that it needs to be able to measure. And these are the required signal-to-noise ratios at L-tip. I do have SNRs for L-max, and there are many other parameters that are used to constrain the system, but I haven't put those on this chart. Relative edge response. Now, one of the things I find about designing land imagers like this is the balance you have to make between relative edge response, that is the image quality, and signal to noise ratio. Fortunately, in the Landsat systems up to this point, it's been relatively easy to meet the signal to noise ratio requirements, which have allowed the designers to really focus on image quality. But there really is a trade there, and you really have to make that trade in designing these systems. So relative edge response, you might wonder, well, what do you mean there's actually a relative edge response that's too good? Well, there is actually, because if you go beyond this limit that I've specified here, you have aliasing. And that's a very bad thing, obviously, so you don't want to go beyond the aliasing limit, because you could easily do that. So those are the relative edge responses and the half edge extent. And again, there are many other requirements that go along with this, but these are just the highlights. So I looked at several different architectures. I looked at a disaggregated architecture, which is basically Atlas plus ILI. I increased the size of ILI to meet the image quality requirements for a smaller 60-meter pixel. And that results in a 28-centimeter aperture, entrance pupil diameter. I think, to sort of cut to the chase on these push broom imagers, on the disaggregated ones in particular, I think these requirements create significant challenges. And the reason is simple. If you're really going to have a disaggregated architecture with a refractive infrared land imager, there's no piece of germanium or zinc selenide on Earth that's going to be large enough to be the primary optical element in that refractive telescope. It's simply not a practical thing to do, which means you go to a reflective approach, which means, in my mind at least, you might as well go with full spectrum, because you're not going to have two relatively large reflecting telescopes on board the same platform. You maybe put them on different satellites. But to me, a more economical approach is to go with a full spectrum push broom imager, similar to the CLI that I mentioned earlier, but with a larger aperture, because we're going to higher quality 60-meter thermal infrared pixels. Another option is to go back to the past, go back to the future in a sense, because this is where I'm going right now. I think a very promising architecture is to update the whisk broom, to use the latest focal plane technology, latest telescope technology in the form of free-form reflective telescopes, latest approaches for scanning the Earth, and basically come up with something that I've called ETM++, just to give it a name. I'm sure it'll never be called that, but that's what I'm calling it, just to have a name for it. Another approach, which is sort of a variation on this whisk broom, is to have a step and stair whisk broom. So now you're starting to make things complicated. Not only the whisk broom that's scanning back and forth across a wider swath than Landsat has had before. Now in this approach, you're stepping and staring. So you might wonder, why would you ever want to do that? Why would you want to incur this kind of complexity? Well, what you're trying to do is compensate for the along track integration drag. And of course, there's cross-track integration drag too in a whisk broom imager. And so you're really trying to get rid of both of those forms of integration drag to improve your image quality, improve your MTF, which improves your relative edge response slope, and which may enable you to make it smaller. But what I found in my analysis is, even if you do the image motion compensation part of it perfectly with your imager, now you're imposing significant requirements on the spacecraft. The current Landsat spacecraft is not stable enough for this to work, basically. And so you need a much more stable spacecraft. It also creates challenges in the focal plane as well. As you're staring, you fill up the wells fairly quickly. We've looked at hyperspectral. It's still in our trade space, certainly, but I think, based on what I've heard to this point, it's less likely to go forward. There's some disadvantages to hyperspectral. You get much more spectral information, of course, but you also end up with some virtual multispectral bands that have much less sensitivity than they do today in multispectral systems. Okay, so this is the impact of the requirements. I've pretty much covered everything on this chart already. I've talked about some of the problems with these different architectures, the challenges really that we would face as I've gone through them. There are different ways to implement it, but I think these requirements, the combination of wider swath and more spectral bands, really create significant challenges for the push broom imagers. For the whisk broom imagers, I looked at two cases. I looked at basically this 28 centimeter compact ETM++, and just for old time's sake, a 40.6 centimeter ETM++. This is a much slower system. You might recall from the beginning of the presentation that ETM+ had a 7 hertz period of scanning. This would have a 0.06 hertz period. So much slower, much more sensitive. The telescope is only about 10 degrees in the along track direction and about 1 degree cross track, which actually makes it an easier telescope than the push broom telescope. It would have full aperture end-to-end calibration as well. I don't think I have time to go through all the details in this chart on the step and stair whisk broom, but I've pretty much given you the bottom line on that already. It's just more complicated. All of these approaches work, and all this, I haven't really provided many of the numbers in this presentation, but take it from me, they all work, some of them with more margin than others. Actually, in the case of this one, there is very little margin in some of the areas, but I think this one is sort of a non-starter at the moment, at least, just because of the complexity. So, of course, management always likes to see charts like this, and I have to say they are a good way to summarize trade studies like this. So what I did was I looked at these different architectures that we've just gone over very quickly and compared them in 5 different categories: overall feasibility, signal to noise or sensitivity really, relative edge response slope, complexity, and size, mass, and power. And I found that the disaggregated push broom just isn't feasible because of the refractive elements being just simply too large for current material availability. The enhanced full spectrum push broom is certainly still a viable architecture. I regard it as being a little less feasible than other approaches, less feasible than I'd like it to be, just because of the challenges with the focal plane itself. But I think technology's improved to the point where we could actually produce a 38,000 element focal plane, either with a monolithic module. That would be hard, but I think it's possible, or with multiple modules the way we've had it today. We would need 13 individual SCAs to cover this swath with one of the focal planes that we looked at. That seems like a lot, but it's actually about the same as what they have today. So it really is maybe even a little bit less complex than what they're flying today. I really feel the best overall approach is this compact ETM++. It's easier in every way than the push brooms, actually. It's easier to make. Maybe as focal plane technology continues to leap ahead, telescope technology continues to leap ahead, the push brooms may become preferred later on. But I think looking at where we are today with technology, this one feels really good to me, the compact ETM++. Step and stair whisk broom has a lot of problems. I think it's achievable, but it's just, to me, it would be too expensive, and really for no real reason. There's you don't have to go to these extremes to meet the requirements of the practical system. You're going to end up with something that's larger and more complex than just the standard whisk broom. So I'm not going to read this chart to you. These are my conclusions, closing remarks, and I'm happy to take any questions you may have now. Thank you very much.
Questions? Got a couple seconds for questions. Anybody questions? Yeah.
One of the things that you mentioned is that you took the Landsat science team's recommendations to heart when considering possible redesigns of what you were originally working on. I know that the USGS has also been aggregating a lot of user data as well.
Yes.
Providing that. How much do you weigh that in comparison to the science team recommendations?
Well, the USGS will determine what the requirements are. And
right.
So the more important driver here is what they come up with in their aggregation. So my understanding is and I don't know what the latest is. I know they've made a lot of progress on their report since July. Their schedule, I think, for releasing that information was the end of this calendar year. So they will determine really what happens. It's really up to the USGS working with NASA to determine what those requirements are. So the science team, is obviously very well informed and very knowledgeable about what they think should be done with land imaging, but they don't set the requirements. So I'm anxiously awaiting the USGS document that you referred to.
Right.
What's the general reason for HSI that you weren't really a proponent of that? Is it because is it an SNR issue? Because they want to take, if you have HSI and you want to create the imagery such that it relates to the archive, you could just aggregate.
Yes.
So what's the main problem?
So I'll tell you how I see it, but then I'll also tell you how I think other people see it as well. To me, it's just like any other approach. You can get there if you make it big enough and design the system appropriately. I do think there's a sensitivity challenge, and there's something that people overlook with hyperspectral. I've run into this myself. With ocean color imagers, where you derive great value from the hyperspectral information, but just because of the realities of a dispersive system, there are certain spectral channels that have relatively low signal-to-noise ratio just because of the solar spectrum. I mean, that's just the fact of life on this planet. And the same thing happens with land imaging. And so what I'm seeing in these communities, I'm seeing some people say, well, I'm not giving up sensitivity. I want better sensitivity. I want better sensitivity, all the wavelengths, et cetera, et cetera. And at the end of the day, when those trades are made, they usually come down on the side of, well, we need a better sensitivity. And so they'll go with approaches that provide that. I think some people have concerns about the data rate that goes with a hyperspectral system, about the real driver in space systems like this, and some people are surprised to hear this, is the ground system. The archiving of all this data, which is incredibly important to do, but when you're archiving hyperspectral data now versus, potentially 200 bands of hyperspectral data versus 11 bands of multispectral data, you're going to have significantly more expense in the ground system. Now, I think ground system costs should go down over time. I think they've gone down a lot, for the same kind of volume of data. And so I think, even though that's a legitimate concern right now, I think over time that concern will be mitigated. But I don't think you can necessarily lose the sensitivity of current systems. It's very rare to take a step back. So I think they'll want to maintain that. And by the way, I think there are other approaches for hyperspectral that are coming along that'll let you have your cake and eat it too, in a sense.
Thank you.
Mm-hmm.
Anything else? Let's thank our speaker. They have, Joe, is that right? There's coffee, et cetera, out in the hall. Is that true?